Okay, I think we can start. That means this is session about lesson 4. It's the second part of chapter 2. Okay? That means in this lesson, I will talk about the second derivative of the function, like what is the meaning and how we can compute based on the graph, based on the table, and still not based on the formulas. We will have nice chapter 3 that we will introduce a nice systematic way how to get the derivatives. Because I know at the moment some students, they're not sure how to estimate the value of the derivative looking at the graph. Now I will add the second derivative. But hopefully we can solve few problems today and a few things will clear out. That means the second derivative, and then a little bit of application, the marginal cost and the marginal revenue. Okay? And the end of the chapter 2 was focused on theory. That's why we will talk a little bit about the continuous function and about the behavior of the function, the end behavior, how functions behave at the end of the domain, which not always, but quite often the end of the domain is infinity. Like the function goes to the, like we can accept all of the numbers, then it's infinity, which we have to find the end behavior. The end behavior in the calculus class we call like a limits. We will compute a limit of the function at infinity, maybe negative infinity, or any other values that are a little bit challenged. Okay, that's me. Let's start. I will switch off my camera because I will look at different screen, okay, but I'm still there. Okay, that's what we have. Oh. Let me do this way, you can see the whole screen. Okay, that means this is section 2.4, the second derivative. That means what does the second derivative tell us? Yeah? We will talk about concavity there. That means we definitely know that if function, actually I can, let's look at this one because this is from the last week. If it's about the first derivative. If function is increasing, then we say that the first derivative is positive. Yeah? Because increasing means that slope of the curve or slope of the tangent to the curve is positive. Then if the slope is positive, derivative is positive because derivative is simply a slope of the tangent line. That means let's say we have a value 5 here, okay? And if I will ask you, can you estimate, let's say 2, can you estimate the derivative at 2 for the given graph at that point? Do you think you can give me the value? I know that we have a few students in the classroom, but it's still, okay? That means we definitely know that derivative is simply slope. Okay? This means if we're looking at the function, it's the slope of tangent line, which means the tangent line, we have to draw it. Or we can say slope of the curve, but it's, I think, more intuitively, we can say slope of the tangent line to function f of x at the given point. And the given point at the moment is 2. Okay? I'm just repeating this because somebody, if you've checked the discussion board, somebody asked on the discussion board. Okay? As we can see, this value, the blue dot is the corresponding value, but we're not looking, yes, we're not looking at this question mark. What I have to do, I have to draw a tangent line, and then approximately, it's definitely negative because we can see function is decreasing. That means it's negative, and I don't know, negative is quite steep. I will say negative 3. Yeah? Don't worry for the exact value. Because when you will check my session from last week, we were doing the approximation, and even I show you the multiple choice question, you will always have the option. Yeah? You will not pick the small number, you will not pick like a positive number. You will know what to pick if you understand the concept. Okay, that means one more time, derivative from the graph means slope of the curve or slope of the tangent line. Okay? And now I will come back to this one. Okay, that means the second derivative. Second derivative is telling me if the function is concave up or concave down. Okay? That's we kind of adopt the same, we're using exactly the same concept, because we know that if the function is increasing, if something is increasing, its derivative is positive. That's me now looking at this shape. I can even focus on maybe on that part, because that part is, let's look at this one, decreasing, and let's look at that part. Yeah? Both of my red parts are decreasing. Yeah? That means the first derivative is definitely negative, and we can see f prime negative, f prime negative. But both of them are bended differently. Concave up, concave down, bended up, bended down. Yeah? And now how do we know that the second derivative has different sign? Because when we will look at the slope, of course, of the tangent, that means this is one tangent, this will be another tangent, and is increasing, its derivative, of course, is positive. Okay? Its derivative is positive. Then slope, of course, is the first derivative. That means I can remove the word slope and I can put f prime. That means f prime and prime of it, it's positive. That's the result. Second derivative must be positive if the slope is increasing. Okay? And of course, the shape, it's like that. Right? And respectively, the same on this side. Yeah? If I will start looking at the slope of the tangent is like 0, and then it's getting steeper. That means, again, I shouldn't say increasing. Based on the value is like, let's say -1 and even more steep, but in the negative direction. 0, -1, -2. That means it's definitely decreasing. Okay, slope is decreasing, and I can say the same. If slope, like whatever I will have, the name, the slope is decreasing, I should say this one up. If the slope is decreasing, its derivative, slope, its derivative must be, of course, negative. And slope, in the calculus way, is the first derivative. That means, again, the output is that the second derivative must be negative for that position. And this position we call concave down. Right? That means the only, I was trying to explain this, but the thing is we have to remember, if the function is concave up, second derivative is positive. Concave down, second derivative is negative. Kind of makes sense. Okay. That's last week. And then let's look at the examples. Okay. We have example number 1. Function and some values that we have to put in the table. At exactly 2 of the labeled points in the figure, the derivative f prime is 0. Okay. The second derivative f double prime is not 0 at any of the labeled points. Okay. They making some comments, and I can explain like why they making these comments. On a copy of the table, give the signs of f prime, and f double prime at each marked point. Okay. Let's maybe start with the value of the function. Okay? Because that's we have to be really like focus. And we only have to give the sign, which I will, of course, use the positive sign for positive and negative for the negative. Okay, that's we can see the whole function, okay? The blue is the function. And if the function, the actual function, is placed above the x-axis, I can label the axis. Everything above, it's positive. Everything below, it's negative, because we do have negative values. That we should be pretty okay with value of the function. Actually, A is, I would consider that A is exactly on the x-axis. That means I will say that at A, function has the value 0. Okay, because that's the 0, and that's the 0. which the other two dots are not labeled. Okay, that means 0. But now point B and point C are above the x-axis and point D is below. Okay, easy. Now, first derivative. First derivative is telling me that E is positive if the function is going up, and if the function is going down, it's negative. We also know that at 2 points, 2 labeled points, first derivative is 0. Okay, and do you think you can tell me where exactly first derivative is 0? Which are the points? A, B, C, or D? Okay. First derivative is 0. This is always the condition for horizontal tangent. Horizontal tangent. Okay, yes, I see the answers. Of course, I can draw horizontal here and I can draw horizontal here. A and B, it's definitely 0. And then function is going down. That means it's definitely at C is negative. And function is going up, at D is positive. We can see the slope of the tangent. Okay, slope of tangent. Okay, that's the first derivative. And this is slope quite steep, is definitely positive. Okay, and then the second derivative, yes, what the second derivative is telling me about the graph? Concavity. Yeah? That means if function is like concave up, bended up, second derivative is positive. That's what we can definitely see. It's point A, it's placed on function at the point that is function is bended up. That means bended up, it's concave up, it's positive. And what about D? D is also placed at the point that the function is concave up. Now, B, it's also obvious because function is definitely bended up, okay? Bended down, of course, concave down. That means B has negative. And C also is placed, because what's happened with C, do you probably, that's what I was referring to. In the question, they telling us that the second derivative is not 0 at any label points, because point C is kind of like a questionable. Yeah, I will be careful to say, because I might consider, depends of course on the formula of the function, that C is the moment that function is changing concavity. Yeah, we can kind of see concave down, and I can consider this concave up. Yeah, that means this is always like the point. Of course, we have to have more tools, more like things to determine that, but they telling us that the second derivative is not 0, because if this will be actually the point that the function is changing concavity, then second derivative at C will be 0. But since they telling us we do not have 0, then I am still consider that this is bended down, concave down, negative second derivative. Okay. Another thing is, I think your textbook is giving that definition. How we can like figure out when the function is like concave down and concave up. If we have this function, yeah, you can always try to draw a tangent line. Okay, that means if you will draw a tangent line, of course, slope of the tangent will refers to the first derivative. Yeah, but I can kind of like draw a few tangents. Maybe here, tangent line, possibly here, tangent line, tangent. I'm trying to show you the point of the tangency as my blue dot. Okay, and let's say below. Okay, yeah, that we do have. And now you can remember that if the tangent line is placed above the curve, always the curve is bended down. Okay, that we can see above, that's above the curve. That's above. Oh, my tangent lines are terrible. one more time, if the tangent line, if you will be able to draw a tangent line and the tangent line is placed above the curve is always concave down. If the tangent line, respectively, it's placed below the curve, we can see below, it's below, then at this point, function is concave up. Okay? That's a beautiful and easy definition. Okay, I gave you a few seconds to digest. Okay, let's keep moving. Example number 2. What we have? Another question to understand the concavity. All together. Okay, a function f has the value at 5, 20, the value of the derivative at 5, 2, and value of the second derivative for all of the values greater than 5, negative. That means second derivative is negative. Yes, quite strong message. Which of the following are possible values for f of 7? And which are impossible? 26, 24, and 22. All right, that means let's see what we have. First of all, what this blue message is telling me? Second derivative less than 0. What will be the shape of the function? Concave down or concave up? Concave, of course, down, because the second derivative is negative. Okay, I can try to draw the scenario. I don't know if I can keep my labels. 5, the value for 5 is 20. Okay, now, I don't know, 6, 7, I'm looking for 7. I definitely know that the function is concave down. Yes, but we can have concave down increasing or we can have decreasing. Yeah? That means I don't know. I don't know if function is like that or if the function is decreasing or increasing. But what I also know, I know that the value of the derivative at 5 is 2. This means that if I will draw a slope of the tangent, if I will draw a tangent, the slope is 2. That means this is slope of tangent. Okay, and since it's positive, I will draw. Of course, I will draw above, right? Above, I will draw above the curve, and this is positive. That means I can't have decreasing function. Okay, because then the slope will be negative. I think the function looks like that. I don't know, maybe like that. And this is slope. Okay, that means the slope is 2. If the slope is 2, how can I figure out still the value of 7? Or maybe my 7 is a little bit far away. Let's say 6, 7. I can try to predict this value. Yes, we're looking for this possible value at 7. Oh, no. We're looking for this value. Okay, 7. But since what I can do, I can try to figure out that value. That's what actually I did originally. This will be the point of 7 on the tangent line. But my point that I'm looking for, it's the blue one. That means the blue one must be less. Let's find the green one, because the green one, we have almost everything. We know this distance. This distance is 2, right? Between 5 and 7. And we have to find the difference. I can say this is value at 7, but it's on the tangent line. Okay, it's not that we're looking for. It's just on the tangent line. That means we will have the value at 7 minus 20. Oh, I don't need a fraction. That means this distance is between the green value of 7 and 20, the difference. And I know that the slope, actually I can refer everything as a green color. That's the tangent line. Because I really would like to take the advantage of the slope of tangent, okay, which the slope of tangent is 2. And this is simply delta y over delta x. That means delta y, the difference in y's is f of 7 minus 20. And then the difference in x is 2. Right? That means now I think we can try to find the possible f of 7. I can multiply both sides by 2, and f of 7 will be simply adding 20 to both sides. Okay, that means this is not, this is not really f of 7, but we can see 24. This is 24. Now I like to put actually 24. And my blue dot is what I'm looking for. That means the real value at 7 must be less than 24. We can definitely see this because it's here. Value of 7 must be less than 24. Not even equal to, because the tangent line will be slightly above. That means everything what is less than 24. Right? We can see less than this one. I can use actually 24, the green color. Yeah, I think we can. That means only 22 if we're looking at the options given. Okay? But please remember, slope of the tangent, that's what I use. And of course, I use the concavity, I use the information about the second derivative. Okay? Always remember. Okay. I think that's a little bit of explanation. Oh yeah, that's another question, but it's the same thing. That's the question and that's the solution, but you can try to cover the solution. I shouldn't show you the solution, and then you can try to answer the question. Okay, you can pause the video, please cover this solution. Okay, you can use like a paper, blank paper. Okay, cover this and try to solve it and try to get the answer. Okay, it's really helpful for your test. Okay, now, I think we shouldn't have this. Okay, that's it. Now we know how to deal with the graphs. Now let's look how we can deal with the values from the table. Okay, the table below shows y as a function of x, so that the function is defined as y equals to f of x. According to the data in the table, is the derivative of f of x negative or positive? And is the second derivative negative, positive, or 0? Okay, that means first of all what I see the difference, the equal distance between x values, 5, 10, 15, 20, 20. That means that's good. Yeah, then I can focus on the values. And now, first of all, do you think function is increasing or decreasing? Because the value is 10, and then it's 16, 25, 35, 50, 75, 100. That means definitely function is increasing. Yeah, the values are getting bigger. If the function is increasing, of course, we know right away the sign of the first derivative. Okay, but now, what about the second derivative? Is this function increasing this way, which means concave up, or is increasing the other way? Increasing this way, concave down. I think I am messing up down and up, and concave up. Yeah, that means this is increasing and this is increasing. That means how we can look at this? We can look at the size of increase. Yes, do you remember? If the difference between the values are getting bigger and bigger, then the slope is getting bigger and bigger, and function is concave up, because we can see the values are getting like higher, faster. This one are getting higher, but slower. The slope is definitely decreasing. The slope is definitely increasing. Okay, and the difference between 10 and 6 is 16. Between 6 and 25, it's 9. I mean, no, the difference is 6. The difference is 9. What did I say? 6. And then 9. And then 25 and 35, I think it's 10. 35 and 50 is 15. This is difference 25, and this is 30, and so on, 45. That means I can definitely see that the size of the increase is getting larger. 9, 10, 15, 25, 30, 45. If it's getting larger, it definitely the slope is increasing. If the slope is increasing, function is slope increasing. Second derivative is positive, because slope means this. Slope means this. If it's increasing, its derivative is positive. And the final output, of course, is the second derivative. Okay, that means that's how we can look at this. And that's actually slope, okay, the inside value. Okay, that means I can remove this. Okay, we can pretend that this is, oh, my graph is crazy, but at 0 we have 10, at least I have, and maybe at 5, 16, okay, at 10, 25. I don't know if my scale is good, but it's definitely concave. Okay, that means I'm really hoping that we can understand how to read the first and now the second derivative from the graph and from the table. Okay, I also typed 2 solutions on the discussion board for question 3 and 5 from section 2.5. You can also check that. Okay, now what I have. Okay, a little bit of explanation. Okay, that means this is the theory. That we also have to be confident and practice the limits, okay? Because we know we didn't really talk a lot about the limits, but limits are the basic concept of calculus. Okay? Because limits means that we calculating something, estimating the behavior of the function. That means this is the function, yeah? And when underneath the limit, we always have the information like what x really does. That means x is not really 0. This means that x is approaching 0, is getting extremely close to 0, and we have to check what's going on with that graph. Okay, that means if we know the graph of the function, like let's say x squared, okay, and I will ask you what is the limit of the function x squared. Actually, I will need space for the last limit. Let me use this one. Okay, that means this is function x squared, and I will ask you how this function x squared behaves as x goes really, really close to 3. Okay, that means this is 3, and of course I can say 3 is at the level that the actual value is. 3 squared is 9. Okay, that means I can say it's 9, and of course it is 9, but what I want you to understand, we're not exactly at 3. That we're not exactly at that red dot. Okay, I can make this. We're not exactly. We're just looking what function is doing as x approaches 3 from the left and the right hand side. That means my graph is definitely approaching that red dot. Okay, it's approaching that red dot, but we're not at that red dot. But what I have to say, yes, I am actually, the function is approaching the red dot. That means it's kind of like a weird thing. We have to know that my blue 9 and my red 9, it's not the same. Okay, algebraically this is 9 and this is 9, but that's what the limit is telling me. We're just approaching the value x, and we're looking how the curve behaves. Okay? Even if this red dot will be removed, I can still say 9, because the function, the blue curve, is approaching that level, 9. Okay, but of course we have comfort because we know the graph. If we don't know the graph, we just have the formula, I think we have to be able to compute like algebraically. That means, let's see. One of the things that we can do, we can take that values like 0, 0, this is 16. But we can take these values and directly substitute, okay? But this only works, and this will be good, the limit, like even this one that I just did. actually I can write, because how, like algebraically, how I even got that, that 9, I can simply say that I substituted, but I need the blue one. Yeah. That means I kind of use we call direct substitution theory. Yeah? But we can do it if the function is continuous at that point. That means if function is defined at this point, we can simply do this. But if the function is not defined, yes, then we have to have, like, yeah, we have the problem. Function must be continuous, like continuity. We have to have continuity at this point. And this one, this function, 1/4 e to the power of negative 4x, we know the exponential function. It's definitely continuous function, and it's defined at 0. That means in order to compute this, I will just substitute 0. And this is e to the power of 0. It's always 1. The limit is 1/4. And I can draw this function. This is e to the negative. That means looks like that. Yx. And actually at the 0, since we have this coefficient 1/4, the value is 1/4. And also the limit. Okay, that's how, because we can see function is getting really, really close to 0. I mean x is approaching 0, then the function is approaching again my red dot. And my red dot is at the level 1/4. Okay, that means that's how we can do 1/4 e to the negative 4x. Okay, that's the 1/4. Okay, this one is probably, I mean, we can still manage, but it's not, let's say, not easy to draw the graph. And what we will do, we will try to get this limit just algebraically. Okay, that means you can see what I did for the easy one. I just plug in 0. That means instead of h, I can put 0. 0 plus 3, 3. 3 squared, 9. 9 minus 9, 0. It's okay. But if I will put 0 in the denominator, actually I do have a really weird fraction, 0/0. We okay with the 0 on the top, we not okay with the 0 in the denominator. Oh no, not at all. That means this is a little bit weird at the moment, okay? But one thing it's helpful, okay? Having 0 on the top and on the bottom, it's telling me that the polynomial from the top and the polynomial from the bottom has a common factor if h is 0. Okay, that means this common factor, h. And in this case, if you will get 0/0 by direct substitution, remember, the answer is most likely not 0. Okay, maybe for 1% of the problems it's 0, but you really have to have the proof, algebraic proof. Okay, the message, the first messages you should see, you should think, oh, we do have a common factor, and I have to find this common factor and cancel out. Okay, that means we have to look at the formula and trying to use a little bit of algebra to simplify. And in this case, probably I can FOIL h plus 3 squared. That means I will copy my limit because I'm still limit, and I will expand h plus 3. Squared means h plus 3 times h plus 3. It will be h squared, 3h and 3h is 6h, 3 times 3, 9. And then minus 9, okay, and h. And we can nicely see the first thing, yeah? And then h squared plus 6h. I will still copy my limit. Okay, and I am factoring h. And that's what I said. I will use maybe different color. H and h, the common factor is gone. And that was the 0, that was the problem. And after finding the common factor and cancel it out, we may use again the direct substitution. That means I can say that the formula that I left is h plus 6, but h plus 6, h is 0, is simply 6. Okay, very good. Also, what we can think that this function is not defined at 0. We can definitely see 0 is not in the domain. I managed to simplify this function to just h plus 6. That means if h is x, okay, it's just the linear function. With the y-intercept 6, this is negative 6. But what is the thing? The thing is, it's not defined. We do have, oh, actually I can leave it like that. We have nothing. We have empty. 1 point is removed at 0 because 0 was not in the domain. Actually, I can put h, just not to confuse you. Yes, h at 0 is not defined, but that's the beauty of the limits. Even if we have empty spot, I can still see that my function, that's what I'm looking for. It's approaching level, the point at the level 6, at the height 6. Okay? And we got algebraic. Okay, and then we have another function. Yeah, let's try. That means first one, second one, and the third one. Okay, let's solve one more. I want to make a nice divider. Okay. What we have, square root of x minus 4, x minus 16. And x is approaching 16. That means I have to find out how this function behaves next to 16. But you probably notice, if I do my direct substitution, square root of 16, 4. 4 minus 4, 0. 16 minus 16, of course, 0. And this is telling me the same, that function is not defined at exactly at 16, but doesn't matter. Yeah? I can still try to find how the whole graph behaves next to 16. Okay, another good sign, which is the same, 0 over 0. This means that the function from the top and the function from the bottom, they do have a common factor at 16. Yeah, let's find this factor. Okay, what we will do, let me remove this. I can say 0 over 0 here. Okay, if you will see the expression with the square root, okay, one of the way to simplify this one is to multiply the top and the bottom by the conjugate expression of the root expression. Conjugate means that I will copy the first term, I will copy the second term, square root and 4, but seeing negative, I have to put the opposite side. That means conjugate expressions are like a minus b and a plus b. A, b, but minus and plus, and the product, of course. And I have to do the same on this side. Now let's do our, oh, not h, let's do our algebra. The two conjugate expressions I have to FOIL, I have to multiply. But let's look at this. A minus b, a plus b. I will multiply a times a, I will have a squared. I will multiply b times b, I will have b squared. And negative times positive, negative. But I will also multiply a times b and again a times b. One is positive, one is negative. That means they will cancel out. That's the only output, answer. That means that means how can I look at this? I can say a, the first quantity is squared, b, the second quantity is squared, and minus between them. Square root of x squared is just x, if x is positive, but we close to 16 is positive. And quantity b, the second quantity 4, it's squared, it's 16, and the minus between them. Okay, we can see x squared, square root of x squared is x, 4 squared is 16. And in the denominator, actually, I will not FOIL, I will not distribute my product. You probably see why, because actually I'm looking for this common factor, x minus 16, because 16 minus 16 is the 0. And now I can nicely see the 0. The 0 is gone. Now I can use my direct substitution. Square root of 16 is 4. 4 plus 4 is 8. 1 over 8. And we can see really nice limit. And the same thing Okay, maybe we will not draw it. I mean, we can still draw it because we did simplify to the function 1 over square root of x 4. That means it's kind of like hyperbola. Okay, like kind of like 1 over x in the first quadrant, of course, because we also have this one, but this is square root, we don't have the negative. And at 16, okay, we still have to remember function is completely undefined. That means its point is removed, but we know what is that level of that dot, 1 over 8. Okay, that means that's the point of the limits. Okay, I squeeze a little bit all of the limits on one slide, but make sure that you know how to compute all of them. First one, second one, and the third one. Okay, you can definitely spend more time on this after the session. Okay, let's keep working. Okay, we also talk about the, as I said, continuous function. That means let's just I copy a few problems from your textbook. Let's just go through all of these functions and say if the functions are continuous on the given interval. Okay. That means first function is x plus 2. Of course, it's the linear function. We have no fractions, no zeros in the denominator, nothing. It's always continuous function. Doesn't really matter what interval will be provided. X plus 2 is the line with the y-intercept 2, x-intercept negative 2, and from the interval from negative 3 to positive 3, I can definitely see it's a nice and continuous curve line. Continuity, you can also test if you would like this way, if you would like to draw a line, and you're not lifting like, if you can draw something with one go, like one try, one go. Yeah? But because as soon as you lift and come back in different place, of course we have this continuity. Okay, that means that's one way. Okay, 2 to the x, nice, 23, 24. Nice exponential function with the base greater than 1. That means this is 2 to the x. Continuity, of course, no problem. From 0 to 10, we do have that part, yeah, if this is 10. Nice and continuous function. Okay, x squared plus 2, also continuous function. We have no problem with quadratic function. X squared plus 2 is just the parabola x squared shifted 2 units up. Okay, and on the interval from 0 to 5, on my graph will be that part. Okay, of course, continuous function. Okay, 26. Yeah, 26, we definitely see we do have a problem at 1. This function is not defined at 1, and when I will draw the function, I have to lift the pen and come back. Okay, that means this is, and 1 over x minus 1 means that we just shift the function. This is function 1 over x, okay, just the hyperbola. But now, since we see negative 1, we shift everything to the left, the whole function, which means also that theoretically the y-axis. That means the function looks like this and like this. I'm trying to keep the space for, okay. And this is definitely 1. We can see it's not, function is not defined at 1. We do have this continuity. However, they're asking us to check continuity between 2 and 3. And we can actually see between 2 and 3, since this interval doesn't include 1, we are fine. This function is actually continuous function. Okay? That's definitely continuous function. And what about 27? 27 is telling me to check the interval from 0 to 2. From 0 to 2, we definitely have 1 inside, 0 and 2. That means this is one part of the function from 0 to 1 and from 1 to 2. Okay? I will use the same graph. That means this function is not continuous function. and because we have discontinuity at 1. Yeah? This one doesn't, the interval is not affected by 1. Okay, and the last one, probably we don't really know how the function looks like. We will probably not expect you to know, but we can see denominator is x squared plus 1. Since it's plus, minus is giving us I mean, we have problems when it's minus 1. But if it's plus 1, it's simply all of the function is defined for all of the numbers, because denominator will be never 0. I can show you the graph. The graph is a little bit weird, looks like that. No? Should be nice and symmetric. That means if I substitute 0, it is 1. And then from interval from 0, I mean any interval will give me continuity. Okay, that's we can, I mean, as I said, we will not expect you, but even looking at the formula, you will tell that we can substitute any number and we do not getting 0 in the denominator. Okay? Okay, let's keep moving. I still have a few problems. I hope I will finish the session in 1 hour. Okay, but we definitely did focus on theory. Yeah, that was more theoretical. Okay, I believe we still have some applications in lesson 4. Yes, the marginal cost and the marginal revenue. That's what we have to just remember, that the marginal cost is simply the derivative of the cost function, and the marginal revenue is the derivative of the revenue function. Okay, and since it's the derivative, we can think about the slope, yeah? And about the slope of the tangent line at the given points. And that means slope of these lines will represent the cost of the marginal cost. Okay. Okay, and I also have this, maybe this one will be more clear. That means the marginal cost is the instantaneous rate of change, okay? Which of course is called derivative of the cost function at the particular quantity. We kind of like use the average. The average rate of change is taken, it's calculated over the interval, but we remember the interval is extremely small interval. That means if it's the difference, I can maybe come back between 1 unit, that's still fine. Yeah? We can compute, because we can see this will be this slope, because we're dividing by 1. This slope, it's kind of like represents the average, yeah, this one, that tangent line. Because when we have really the difference, it's this one, I believe, between this point and this. If we have 2 points, the difference in 2 points is, and dividing by number of units, which is 1, it's the average. But we're really looking at the tangent, because that's the marginal cost. But in this case, we kind of saying that they are the same, okay? Because this will be the slope exactly at 100, but we do not have sometimes enough data, especially from the table or from the graph, that we will use this small interval. Difference between 100 and 101, we consider as a small interval, yeah? to estimate the instantaneous rate of change. Instantaneous rate of change is derivative, is the slope of the tangent. Okay, I think we know that instantaneous rate of change at the point, it's simply derivative, and of course, slope of tangent line. Tangent line at that point, the same point, of course. Okay, also you can pause the video and read this. Okay, let's look at a few questions. If the revenue and the cost function R and C are given by the graphs, that's revenue, that's cost, sketch the graphs of the marginal revenue and the marginal cost, M, R, and C. Okay, revenue. Looks like a nice linear function with the constant slope, because the slope is the same for every single point. If I will plot the tangent line, which actually tangent to the line is the same line. That means this slope is constant. Okay, slope constant, And what we can say, the slope is like 1 maybe, which means the marginal revenue, or I can say R prime, it's constant. It's, let's say, 1. Okay, and we can see that will be, okay, this is that value, 1. Let me put 1. Okay, constant quantity. Okay, this one is not really constant, because if I will draw a few tangents, then the slope is changing. That means this, let's draw the tangent here. And then let's draw kind of like something, what I can do, this one, and let's draw here, let's draw here. Yeah, we have this interesting, however, I think that's what I'm looking. At this point will be point that the function is changing concavity, right? Because it's concave down and then concave up. But what I see, this slope is quite steep, yeah, and even if it's quite steep, that means the value of the derivative, it's huge, okay? But then the slope is getting smaller and smaller and smaller. And this will be the point that is a minimum slope, because starting from that point, slope is increasing again. That means the values are big, 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 big. I can maybe draw the slope, corresponding slopes are big, and it's decreasing, and it's attaining some kind of minimum, and then it's again growing, okay? That means that's how the derivative looks like, which of course will be the marginal cost. I can say C prime. Okay, that we can see big values, because all of these dots represents the slope of the tangent for the above graph. Okay, and then minimum value of the slope, and again the slope is increasing. That means everything, if you have to determine the value or the graph of the derivative, think about the slope of the tangent line to the original graph. Okay. Marginal revenue. Oh, okay. I didn't want you to see this, but it's okay. Let's solve it. Do I have the, okay, I have the other one. Okay, I will skip the other one, but let's just solve this question. It's a little bit of application, and probably it's the common sense, because we're not really, everything is given. Okay, let C at Q represents the cost, and the R and Q represents the revenue in dollars of producing Q items. Suppose that the cost of 100 to produce 100 units is $4,000. The revenue, yes, of selling 100 units is $5,500. If the marginal cost at 100 units is 20, and the marginal revenue at 100 units is 24, approximately how much profit is earned by producing the next item, the 100 first? Okay? That means, of course, profit, it's simply the revenue minus the cost, 5,500 minus 4,000. We do have $1,500. That's the profit. Profit, of course, producing 100 items. Okay, and then the marginal, okay, marginal profit. It will be the marginal revenue minus the marginal cost. 24 minus $20. $4. Okay, that means we can see like adding one more unit of the production when 100 units are being produced and sold adds approximately $4 in profit, because this will be the rate how the profit is changed. Okay, that means we can see, I can uncover now, producing and selling 101 units yields to the profit of $1,504, because we can simply add them together. Okay, that's me, no problem. But make sure that you know, yes, how to navigate And I believe my next question is almost the same, and I just change things. And I think this is my last question. Okay, that's been perfect, almost in 1 hour. And as always, I know that almost everybody is watching the sessions, watching the recording. Make sure that you understand every single question, and then you will be definitely successful. And of course, try to understand the concept. Yes, not exactly like the same. If we change the numbers, if we change the functions a little bit, I still want you to be like confident, okay, and like to have an idea of the concept of calculus. Okay, thank you very much, and you will hear from me next week.